Number 14, our given differential equation is dy dx equals 1 plus the square root of x all over 1 plus the square root of y. And again, we're finding general solutions. They might be defined implicitly or explicitly. Okay, so we can definitely just cross multiply. So we have 1 plus the square root of y dy equals 1 plus the square root of x dx. And oh, this is nice and easy. Our we have our function of y, right? Our f of y dy, g of x dx. Okay, so we've separated our variables, right? Here is, right, these variables are separated. We can integrate, but before we do that, we can definitely rewrite these radical functions as powers because we're going to use a power rule. So we have y to the half dy equals y plus, or 1 plus x to the half dx. And now we can integrate, right? And we have, right, that's, we don't have to write the parentheses, but that's really what it's saying. So I'm going to go ahead and write, I'm going to split up the integral. See, the integral of 1 dy plus the integral of y to the 1 half dy, and then similarly dx plus the integral of x to the 1 half dx. Okay, so now we integrate, and we have, okay, so this part, well, that's just y. Plus y to the, well, it's 1 half plus 1, which is 1 and a half, or 3 halves. So that's going to be 3 halves divided by 3 halves, but that's the same thing as multiplying by 2/3, equals, and then I have x again for the sky, and finally plus, and similarly half plus 1, we have x to the 3 halves, and again we're going to multiply by 2/3. And then I'm going to add my constant of integration. If you wanted to, you could add, you could add, C1, C2, C3, and C4, and then this would be the sum of C1 through C4. But I'm just going to write C. Hopefully, by now you get the idea. It's just some arbitrary constant. Okay, so the goal is to solve for y if possible. So can we solve or isolate y explicitly in terms of x? And here the answer is no. And to simplify this a little bit, I'm going to multiply everything by 3 because I can, right? We're allowed to do this just to make it look nicer. So we have 3y plus 2y to the 3 halves, 3x plus 2x to the 3 halves, plus, again, 3c, but I'm just going to call it c. And hopefully this is a little bit clearer that you can't, if you try solving for y, that's actually a good exercise. I mean, if you try solving for y in terms of x, it's not going to work out. Because in order for it to be explicit, one input, if I input 1x, it spits out one output. But when I input 1x, it's going to spit out more than one output. So it's the function is not one-to-one. So that is your, this is our general solution, right? And which is defined implicitly, right? So, whoops. Keep getting that wrong one. Okay, this solution is defined, right, implicitly, and this is how your book has the answer, which is completely fine, but in the next section and in chapter 2, there's another way of writing this, and I just want to point this out. So if we solve, solve for C, right, above, if we solve for the constant, I'm just literally subtracting, right, 3x and negative and 2x to the 3 halves from both sides. So I would have 3y plus 2y to the 3 halves minus 3x minus 2x to the 3 halves equals some constant. So it obviously means the same thing. I just solved for C. And remember in the beginning of the section, right, we had this capital h of xy, right? Hopefully that makes sense that this is a function of x and y, right? It's a function of x and y. We cannot write a function just of x in this case if we try to solve for y. And that's pretty much it for this problem. Here's your implicit solution.